So now we're going to do the conformation analysis of cyclocompounds, okay, or cycloalkanes. In cycloalkanes, there are cyclopropane, cyclobutane, cyclopentane, and then cyclohexane. After that, the rings get very big and floppy. So these are the common rings that we talk about initially. And cyclopropane is least stable, and cyclohexane is the most stable, okay, of all the rings. And this is because cyclopropane has high angle strain, okay, and so the stability increases towards the cyclohexane ring. So when we look at the conformers, we actually look at only for cyclohexane. That's it, okay. Cyclohexane rings do not exist like this, okay. We draw them out like this, but not real structure, okay. That's not what they exist like. They actually exist in different conformations because they're floppy and they can move around, and so therefore their structures will actually look like this, okay, which is called a chair conformation, okay. And so this is what it looks like, and then you have the hydrogens coming out on all the carbons, which we will draw out in a minute. But that's a chair conformation. There is another conformation that it exists in, and that is called the boat conformation, but we don't really study this one, okay. This is less stable, okay. So within the chair, there are two chair conformations and only one boat conformation, and we don't do the boat conformation, remember that, okay. So when we talk about conformation of cyclohexane, we're only talking about the chair conformation. So let's go ahead and draw the chair conformation. The way you draw the chair is by drawing parallel lines, and I draw my parallel lines like this first, okay, and then parallel line, and then third parallel line, and the third parallel line, okay. So here's how you get the cyclohexane. And the flip of this is when you rotate this ring towards this side, which means this carbon goes here, this carbon goes there, that carbon goes there, and that carbon goes there. This carbon goes here, okay. So that is what the rotation is going on. That's the flip, which means now I'm going to draw my parallel lines like this, okay. And then we have the bonds going like this. That's the second parallel line. And then the third parallel line is like this, okay. So that's how you draw the cyclohexane in the second flip, all right. Carbon number 1 and 2, I will just take the 2. Carbon number 1 comes down here and 2 goes up here, okay. That is how the flip actually occurs, which is what the rotation is then. And then you can take it right back and get the other flip, okay. So these are what we call chair conformers, okay. Now for the hydrogens, okay, on the chair conformer. So here again is our chair, and we have 2 hydrogens on each carbon. So I will draw my axial hydrogens first, okay. This is axial, this is HA going up. And then the second axial hydrogen is always going to go down. So I'll label that A. The next one will be going up, HA. Next one will be going down, okay, HA. And then going up, HA. And then going down, and I don't have any space, so I'll just do it a little slightly here, HA. Okay, so that is my axial hydrogens. Now I'm going to draw my equatorial hydrogens. The equatorial hydrogens are in the equator, but not exactly straight, horizontal. They actually go at an angle, okay, down here. So H equatorial, this is not helium, okay, please remember. Next equatorial is going up, so H equatorial. This is axial going up, so this is equatorial going down. This is axial going down, so equatorial is going up, equatorial going down, and axial was going down here, so equatorial is going up. Okay, when you do the flip of this, the other conformer, so after ring flip, all the axial hydrogens become equatorials. So therefore, up axial hydrogen becomes up equatorial hydrogen. Okay, that's how it is. So keep that location the same direction. Okay, all right, so let's draw one first, and let's take one methyl. Well, actually we don't need the methyl, so methyl cyclohexane. Okay, so let's draw the structure for that, and here is my ring. CH3. I'm not going to draw my hydrogens because otherwise it will get too cluttered. Okay, so my methyl group right now is in the axial position, and I will draw the other flip, and remember, in the other flip my axial is going to become the equatorial. All right, so here is that and that, there. Now since this is axial going up, my equatorial methyl group also has to go up. All right, now let's look at both the structures and see which one is more stable. And equatorial methyl group is more stable. Okay, why is it more stable? Because of less steric hindrance. Okay, and where is the steric hindrance coming from? The steric hindrance is coming from all the hydrogens. So for example, if we look at the less stable structure, you will see that you have the methyl group over here. You also have this axial hydrogen going down, this axial hydrogen coming up, this axial hydrogen going down, this axial hydrogen going up, and this axial hydrogen going down. Okay, so these three will start interacting with each other, and there is less space then. Okay, so this is a shared space, and because of that, this causes more steric hindrance. Okay, so therefore this is less stable. The equatorial, on the other hand, is outside, and so there is nothing out here, and therefore this is more stable, less steric hindrance.